In this video, we're going to go over a Nernst equation problem where there's a little extra at the end where you have to go to KSP, and this one causes a bit of confusion, so I thought it was a good example. So let's go ahead and just write out the cell diagram that goes with this problem first of all, and then we'll go from there. So it's silver, solid, silver bromide, solid, bromide minus salt bridge, silver ions, aqueous, and finally silver. Look at that, we have a silver electrode at both the anode and the cathode. That's okay, we can do that. And what they're saying is that E0 for the cell is equal to plus 0.73 volts. And what it wants to know is KSP for AGBR. Okay, so on the face of this, there's a fairly flippant way we can answer this. We can say, okay, delta G standard is equal to minus NFE standard. So that would enable me to take this, put it into here and get delta G standard. And we also have delta G standard is equal to minus RT natural log of K. So we can set the two equal to each other. We can say minus NFE standard is equal to minus, oops, should be a T here, RT natural log of K. Minuses go away. And then we have natural log of K is equal to FE standard over RT. Let's make that look like an F. And then, of course, we then get K is e to the power of FE over RT. All right, so in theory, if we've got RE standard for the cell, then we can get K for the cell. But notice that when we do this, this is K for the cell reaction. Okay, because E standard is for the reaction in the cell. So to go back to the top of the problem, we'll see why it's not quite as straightforward as just plug and chug like this. It's almost that straightforward, but there's an extra piece to look at. Anytime you're looking at one of these, you want to make sure that you actually can see what the reaction is. So obviously, yes, cathode is over here, right? Reduction on the right. Anode's over here, oxidation on the left. And it's pretty obvious what's going on here. Silver plus an electron goes to silver. But why don't we actually go ahead and write the half reactions out? You might say, why bother doing that? I already know what the E standard for the cell is, and that's what I need to go ahead and get K. I don't need to find E non-standard. It's standard anyway because it doesn't give me any conditions. That's true. But let's go and look at these two half reactions. So let's go ahead and write them out. I'm going to have move this equation up the top of the page, but that's okay. So first of all, we've got the reduction, silver, okay, AQ, plus an electron goes to silver solid, okay? So that's my reduction. I could even look up the reduction values in a table of reduction potentials if I wanted to, but I don't really have to because I've already been given the standard cell voltage, so I don't really have to look that up. But let's focus back on the equation again. The other equation is a little harder to figure out. This one only had two pieces. Let's go back up here again. This one only had two pieces. So here it is before, here it is after. This is the electrode, and it's part of the cell reaction. There's only two pieces to this. But over here we've got three pieces. It's not so easy to see what's going on. So what I'm going to do to help myself is I'm going to get another pen, and I'm going to label oxidation numbers. This will help me figure out the half reaction, and you can do this anytime you're not sure what's going on. Label with the oxidation numbers. Over here it was obvious, right? It was +1 and it went to 0 because that's all you had. You had just the silver. So let's go over here and label oxidation numbers. It's not that hard. This is silver solid, so this is 0. This is silver bromide. Oh look, there's bromide. Well, that's -1. So you know that one. Silver bromide. Bromide ion is -1. So this must be silver +1. So we've just figured out the oxidation numbers. Now if you look at that, you might say, but this isn't really in the order in which things happen. This is true. This does happen sometimes, especially when you have what's known as a composite electrode, and this is an example of one. These two pieces would actually be inside of the electrode itself. You know, if this is the electrode, it would be, there'd be some stuff inside of here and then a wire. And then this is part of the solution on the outside. So there is some logic as to why they write it in this order. But don't necessarily assume this is going to be in perfect order as to how you find it in the equation when you've got more than two parts to this side. There's three. So that's why we use these to help us figure out what's going on. So you can see what's happened now. There's got to be an oxidation over here. So we can find it. There's silver 0, there's silver +1. So this tells me that this is the before and this is the after. So I now know where to put these two pieces. I need to put this on the left and this on the right. So let's do that. All right. So we've got Ag solid. And then over here, we've got AgBr solid. All right, not finished. So let's go back up here. All right, the last thing is bromide. And it was -1 and -1. It's not reduced or oxidized, but I need mass balance as well as charge balance. So I'm going to have to put my bromide in. So I need to put it over here. Okay, now remember this one's reduction, we need an oxidation. Remember this was at 0, this is +1, there's a -1 sign here, this is no charge, so both those things argue there should be an electron here. Now we'll do what we always do and make sure we have a proper balanced equation. The electrons go away. Let's write out what we've got. Ag plus, oops, there we go, aqueous, making sure I had that down, plus bromide minus aqueous. Wait a second, we can cancel something else, can't we? Silver solid, silver solid. All right. AgBr solid. That's the reaction going on in the cell with the diagram that looks like this. Now you see why I had you write this out. Because if you look at this, KSP, is that KSP? Think about what you've learned about KSPs. Nope. This is actually the reverse reaction for KSP, right? KSP is supposed to have solid on the left and then aqueous signs on the right. Well, this is around the other way. KSP is, the reaction is going to be AgBr solid goes to Ag plus AQ plus Br minus AQ. Now, another thing we can think about, KSPs are small, which means that they are much less than 1. So if you think about it, if it's much less than 1, delta G standard is equal to minus RT natural log of K. So this follows, therefore, that if we have a small value of K less than 1, delta G standard is positive. In other words, something that's non-spontaneous. All right, that would be consistent. The delta G that goes along with the KSP is going to indicate non-spontaneous. It's not very favorable for this to form into solution, to dissolve, I should say. It's much more favorable for a precipitate to happen from the point of view of the spontaneity. So there's another thing we can say, since delta G standard is equal to minus NF E standard, this also tells us that, given the above, that E standard is negative. Once again, non-spontaneous. This negative value of E standard that we would expect comes from the fact that delta G is positive and is consistent with the fact that we have a small KSP. The stuff's not very soluble. All right, so if the E standard is negative, if you remember at the beginning, the E standard for the cell that we had was positive. So there's two ways to do this. Once you've come to this conclusion, and again, you don't really have to write all this out, you can kind of just run through the logic. What you really need to write out is the part up here. Here. This is the part you really need to write out. Oops. So that you can realize this is what the cell reaction is. This is the part you really have to write down to make sure you know what the cell reaction is. This other stuff here, I've just kind of written down what we've already known and just reviewed. So there's two ways to finish. One, what we can do is flip sign on E0 given as it is for reverse reaction to the one desired. So let's see, that would be E0 equals negative, and then the value that I'm bringing from the top of the page, plus 0.73 volts. So that's minus 0.73 volts. And then we can do K equals E to the minus F E standard over RT. Well, that's exponents. E to the power of all this. And that 0.73 volts will go right in there. Or, number two, we can say except E0 is for reverse reaction, still use it to find K, then use K tricks. Remember K tricks from when we did chemical equilibria? If I know the K for the forwards reaction, then the K for the reverse is 1 over that. K forward is equal to 1 over K reverse. That's the trick that we're going to use. And so you can do that too. So it doesn't really matter which way you do it. Either way you'll get the right answer. Let's just do this one, just for the sake of completion. All right, so K equals E to the F E0 over RT. So I'm going to use the original value. So F E standard over RT. Let's see what we've got there. 96,487 joules per volt mole electrons. Quite a lot to write there. Times my E, which is plus 0.73. Again, I'm accepting that this is going to give me the K of the opposite reaction. R is 8.314 joules per mole Kelvin, and my temperature is 298 Kelvin. How do I know it's 298 Kelvin? Because it said it in the problem. All right, so let's go ahead and do our calculator. 96,487. Yeah, calculator. 96,487 times by 0.73, and then we're going to divide it by 8.314, and we're going to divide it by 298. So we get 28.4292. Let's grab another digit. Lots of digits is good. 6 is a very good idea on Quest. All right, so we've got that number, and now we just need to do E to the power of that. Okay, so let's get our E. This is where you get, originally, those of you who've jumped in and done this, you probably got to this point. Okay, so now let's do E to the power of that. E to the power of answer equals, here we go. So E to the 28.4292 comes out to be 2.221599. Again, put in lots of sig figs because you're playing around with logarithms and reciprocals and things. Don't cut it off short. And now, using K tricks, KSP equals 1 over this particular K that I've just found. So I just hit the reciprocal button, and I get 4.50 times 10 to the minus 13. 4.6 times 10 to the minus 13 is the choice, and it's the only one that's even vaguely close. Notice it's minus 13. Let's draw a little line here. So this is small, which is consistent with what we expect. And the reason I don't get 4.6 is probably because I used a slightly different value of the Faraday, or I didn't use 0.15. Like I said, exponents, logarithms can really compound that. So that's why you always want to keep lots of digits. But we have definitely got a number that is much more consistent now with a KSP. So that's one. If the other way I would have done it is I would have just been doing all this math, but that would have been a minus instead of a plus. And so magically I would have come out with this number originally. So that's the way through that. So the trick is, unless it's absolutely blatantly obvious from the cell diagram, as in there's only, 2 pieces on the left and 2 pieces on the right, go ahead and write the cell reaction out. That way you just make sure it's what you intended.